Well, here goes nothing. As I left my my phone, my camera at home today, so I'm working off this allegedly smartphone. I went to the Dollar General to buy a charging cord, so it's got some amount of power. It should last, but anyway, let's get into it. So I wanted to describe what we mean by polynomials and indeterminate. So up to this point in your mathematical existence, you probably really freely interchanged the concept of polynomial expression and polynomial function. You know, like a polynomial function is something that is described by a polynomial, and really the rule for the function is described by a polynomial formula. But you can really always think about plugging numbers into the variable of the polynomial, right? Mm-hmm. In contrast, what I'm about to describe to you here is the concept of indeterminate. Indeterminates are not variables. They are just essentially placeholders. Now, we have a mechanism for evaluating those, but that's not, we don't actually think of the things comprising the polynomial indeterminates as variables. Now that may just sound like sort of a philosophical, bit of nonsense, but I'll do it carefully here. Sorry, I had to shut the door. My bad. Okay, so let me start by defining for you guys formal power series over a ring. So R is going to be commutative ring, all right, with identity 1, all right? And so here's a definition. Formal power series is something of the form sigma from the natural numbers union with 0 to the ring. And you can write sigma of j equal to s sub j, as we often do, or you could just write it as this: sigma is equal to, s0, s1, s2, and so forth and so on, right? You could write it sort of using that sequential notation. And here, the s sub j are the coefficients of the formal power series, all right? Okay, so what's a polynomial? By the way, the reason we call that a formal power series really isn't clear until a little bit later in the lecture. I'll try to circle back to it when I get there. If you could remind me when I get there to circle back, that'd be helpful. Definition. A formal power series sigma right, like that, over R, okay, is a polynomial over R if there exists J in the excuse me, not J, there exists M in the positive integers, right? Such that S sub J is equal to 0 for all J greater than M, right? If sigma is not equal to, 0, all zeros, right? So sigma is not the zero formal power series. Then, well, this is, I'm sorry guys, I keep losing track of where I was reading. Let me just say that this, sigma with all zeros is the zero polynomial. Okay. And if sigma not equal to the zero polynomial, and we're also just going to denote this by zero because, you know, why not? So if sigma is not the zero polynomial, yeah, and S sub n, rather S sub, I'm very sorry guys, I'm having trouble forming sentences at the moment. Then and sigma is a polynomial. All right. Then the smallest n such that what? S sub j is equal to 0 for j greater than n is known as the degree of sigma. So the degree of sigma equals to n. Another way to say that is, you know, S sub n is not equal to 0 and, you know, no, you know, S sub j is not equal to 0 for j greater than n, right? I mean, I don't know. I'm having trouble saying this simple thing. The degree of a polynomial. You guys know what it means. So
Yeah,
like,
it's how many times it crosses the x-axis geometrically.
oh no. R is not the real numbers. R
Oh yeah. Oof. The degree of it is ooh, man.
So it's, you know, the degree is defined by the leading coefficient, right? That's the highest, you know, as far as, in our current notation, as far as you can go over and you find something non-zero, that's the degree. So like,
Okay, so it's exactly how I think of it in pre-calc.
Yeah.
Okay,
Yeah.
okay.
Yeah, so like, for example, I'm sorry, this is not complicated, I'm just being a doofus here. You know, sigma is 1, 2, 3, 0, 0, 7, right?
Yeah.
So this is S0.
Yeah, so that'd be degree 5.
1, 2, 3, 4, 5. This is S5, right?
Yeah.
And if these are all zeros past this point, you know, to be clear, then the degree of sigma, like you said, is 5.
Okay, I got you.
And another example, let's use R equal to Z6, right? So we can have like sigma 1 is 1, 2, 3, you know, zeros beyond that, and sigma 2 is 0, 2, 3, and then zeros beyond that, right?
Mm-hmm.
So here the coefficients are being taken from Z6, right? So just to, you know, what would sigma 1 plus sigma 2 look like? And what would sigma 1 times sigma 2 look like? I haven't defined those yet, so don't answer just yet. Definition. If, so we can define the addition and multiplication of polynomials. So if sigma and tau are in, and so by the way, notation, like this set of all polynomials, in our, over R is R square brackets X. So I've already been using that notation, but I never really defined it systematically as I'm doing at the moment. So if sigma and tau are in R of X, then and sigma has S coefficients, you know, and tau has T coefficients, then sigma plus tau, you just add the coefficients, right?
Yeah.
And sigma times tau, that's a little more complicated. The way that works is, here's the definition. You multiply the constant coefficients. For the next one, you have S0 T1 plus S1 T0. The next one up, you've got S0 T2 plus S1 T1 plus S2 T0, and so forth and so on. The formula for the kth term, I call that a sub k, right?
Mm-hmm.
Then your a sub k is by definition the sum I plus j equals to k of si tj. So it's all choices of I and j which sum to k. That's a sneaky notation for all possible pairs I and j that sum to k.
Okay, so why, how does that happen?
Like A2, it's not clear yet. This is just a definition.
Okay.
S0, you know, T2 plus S1 T1 plus S2 T0 is this pattern. The only way to get 2 is 0 plus 2, 1 plus 1, or
Yeah, because they're opposites, like,
plus 0.
it's oppositely adding.
So, so you know, you can, there's this obvious question here, problem.
I understand.
Why is sigma plus tau and sigma tau actually in R of X again, right? How do I know that when I add these two things together, I get another polynomial, right? What does it take for it to be polynomial? It takes for it to be a polynomial, it's a power series, a formal power series that terminates at finite order, right? At some point it stops being non-zero and it starts being 0. And so let's go back to this example just before we address that question. So sigma 1 plus sigma 2 here is, you add the coefficients, right? So we got what? We got 1, 2 plus 2 is 4, but remember 4 mod 3 is 4 mod 3 is 1, so we got 1, 1. 3 plus 3 is 6, mod 3 is
2.
No, 3 plus 3 is 6, mod 3 is 0. In fact, I'm an idiot. Can I go back here and change this, guys? I wanted to put a,
Absolutely not.
oh man. I'm gonna change one of those to a 2, so, sorry. So yeah.
That is one demerit on your evaluations.
It won't be the only one. So 1, 1, 2, and then 0's past that, all right? And when I multiply them, what do I got? I got, all right, so the first coefficient is the product of the product of the 0 ones. So 1 times 0, 0, right? And then next I do S0 times T1 plus, you know, S1 times T0, so I get 2. All right? And then for the, like notice something here. I wrote, I could have kept that 3, I'm a dummy. Why am I doing mod 3? What's wrong with me? Good night. This is mod 6. You guys, don't let me do that. 1 plus, we fix it. 2 plus 2 was 4. Dumb. Me, not you. 2 plus 3 is 5. And I wanted to keep that 3. I'm gonna put it back to 3 again. I'm so sorry. 3, I'm going back to 3 again. 3 plus 3 is 6, which is 0. That's what I wanted to have happen there. My bad. Okay, so we're still okay for that, and then 2. Okay, fine. Now we gotta figure out what's the third term.
So 3 times 0.
Yeah, we're supposed to do, let's see here, like 3 times 1 plus 2 times 2, right? Plus 0 times 3, I think.
Which is 7, which is 1.
Which is 1, okay. Is that right?
The fourth term, yeah, I think that's usually is.
Man, that feels wrong.
So 0, and then that would be 6, that would be also 6, that would be 0, yeah.
Oh, okay,
Yeah, it's 12.
wait a minute, what?
Like if you multiply sigma 1 times sigma 2,
Yeah.
the out to past
It's not 0 past there, that's I'm wrong about that, right?
well, it'd be 12.
Next is 12?
So 12 mod 6, 0.
But what's the next one past that?
Let's see. So 1 times 0, 2, 0, 3, 9, 0, 0, it'd be 9, 3.
3, alright.
I think.
I'm gonna trust you.
Oh man, pressure's on.
And the only way to get 6, right? Actually, this is 0, 1, 2, 3, 4, 5. To get 5th order, you have to do
1, 0, 2, 0, 3.
So yeah, I need to. This is 0, 1, 2, 3. All right. So in terms of like the coefficient numbers.
So you need 6 out to 6. So 1, 0.
Where are we?
You're trying to get to the 6th term.
0, 1, 2, 3, 4. We're at the 5th.
Okay.
The 6th one is the 5th.
Yeah.
Degree.
So
term.
4. So there's 2 zeros out there. So it'd be 1, 0, 2, 0, 3, 0.
Well, the only way we can get to it is either 2 plus 3 or
Yeah.
like it's just these two. You know, it's S2 T3 or S3 T2, both of which are 0. So like that, and past that, you can't get coefficients summing to 6 because you have at most have 2.
Yeah. I get it. I was just crossing them off in my head so I didn't lose track.
You're fine. I'm not 100%. I mean, I've taken your word on it here, like, you know, this 0 and this 3. And I'm not saying you're wrong. I'm just saying I haven't checked those in my mind either. Let me just check on this one. 0, 1, 2, 3. All right. To get the third one, we either need 0, 3, or 3, 0. Those are nothing. And then this gives us 1 and 2, or 2 and 1. So again, that's 6 plus 6, which is the 12 you mentioned, which is 0. Great. All right, enough about this. So the point here is, this illustrates something, right? The degree of sigma plus tau is what?
1, 3, 4, or plus tau. Oof. That's
So
2.
what was the degree of sigma 1 here? It was 2.
Yeah.
The degree of sigma 2
Was 2.
is also 2. What's the degree of sigma 1 plus 2?
1.
It's 1, right? So this is generally less than or equal to the maximum of the degrees of sigma and tau. Just think about that for a second. It's like, it's very obvious why that should be true. You might be tempted to say it's equal, but that's not the case, because you can have the conspiracy of leading coefficients like killing each other, like happened here. And so like, while these both have degree 2, when we added them, we got something degree 1. Because the leading coefficients canceled out.
See, I can only think about in real numbers.
Oh,
It's like
it's like x plus 2, plus 3 minus x.
Yeah, like you can't go higher. You can kill them all. You can kill
Right.
the top terms off, but you can never go higher.
That's true.
So like, so since we're talking about a ring, which is commutative, and like, since we're talking about a ring, can we still say that's true? Like, you can't add higher rings.
You can't add 2 polynomials and get something larger degree than what you started with.
Yeah.
Now, when you multiply them, on the other hand, right, what's the degree of sigma tau? Well, it is less than or equal to the degree of sigma times the degree of tau, right?
Yeah.
You see, you could have,
Yeah, that makes sense too.
you could have equality there, but we didn't in our example because, what was this? Or did we?
2 times 2 is 4. So yeah.
Oh, we actually did have it here, didn't we?
Uh-huh.
How did that happen? I questioned this 3.
You can do it.
And then you question that 3, because that's 4. How do we get 4? We can either get 2 with 2, which is 9. Well, yeah. Dang it.
That's my win for today.
That does not make sense to me.
Look, it's 1.
Oh, yes it does, yes it does.
1 0 2
It
0.
goes back to the original confusion I had of changing 6 to 3 in my mind.
Yeah.
That's
The
the problem.
only thing you got left is a 3 3 term and the
Yeah.
2 2 term. Or the 2 3 and 3
So
2.
my apologies. That's fine. So yeah, in fact that does have equality here, right?
So that's only if your terms don't cancel each other out.
Yeah, to give you a simple example where the degree is less than, here's one. If we had, I'll use Z6 again, yeah?
Okay.
And this time, sigma is, 0, 2, and then zeros. And then tau is 0, 3, and then zeros.
Yeah.
Right? You multiply sigma tau here.
2 3 6 0.
Let me put a 1 on one of these. A 1 there.
Change.
So, what happens then?
0 0 2 3.
Yeah, so 0 to start with, and then what?
2 3 and then 1 times 0. 2 times 3 1 times 0.
Well, we have, oh, I'm an idiot.
I'm starting with the S1.
The degree of the product is not the product of the degrees. I'm a moron. Everything I'm saying today is wrong. Plus the degree of tau, right? If you multiply a second order polynomial times a third order polynomial, you don't get a sixth order polynomial. You get
we're working
2 plus
two.
3, which is fifth order
We're
polynomial.
working in 2, so this mistake is granted.
So
We're working in 2s.
so 0, and then the next thing we get 2, right?
Mm-hmm.
And then how about the
1 times 0, which is 0.
the only way to get 2 here is from the 1 and the 1, right? 1 plus 1. So like, which is 6, which is 0, like you said, yeah. So the degree of sigma tau is 1, and the degree of sigma is 1, and that's equal to the degree of tau. So here, we do not have equality. We have the degree of sigma tau is less than the degree of sigma plus the degree of tau, which is 1 plus 1, which is 2. 1 is less than 2.
Where are you pulling the 2 from in S1?
Where am I pulling the 2 from?
Yeah.
This one?
Yeah.
So,
Is
0,
that-
1, 2, so, to get 1,
Oh, okay. You change it to 1.
I can either, yeah, put that 1 there, so it's that.
Okay, yeah, I got you.
Alright, I'm so sorry, I'm wasting all kinds of our time at the moment, my bad. So anyway, you can clearly see that, because if we think about degree for a second, since the degree of sigma and tau are finite, likewise the degree of sigma plus tau and sigma tau are finite, going to show that the sum or the product of polynomials is again a polynomial. Yes, sir?
No, I'm just still doing math in my head.
Oh, okay.
S1 T. Okay.
Alright, so. Let me not try. I'm trying not to spend the entirety of class on this, which is, you know, interesting, but also maddening. This notation is very cumbersome, isn't it? Right? It's very cumbersome. It's not our usual notation for polynomials at all, is it?
No.
It is not. So let's consider a polynomial. Sigma in living over x again, okay? And we're gonna write sigma equals to, let's say, S0, S1, all the way on out to, let's say, S of n. And then zeros past there, okay? Then we can rewrite this as S sub 0 oh, I'm sorry, I'm forgetting something. I'll just make a comment here. My bad. Sigma plus tau is equal to tau plus sigma, and sigma tau is equal to tau sigma. Exercise for reader. To prove those, all you have to do is write down the definition and essentially switch the order of the s's, the s sub j's and the t sub j's. It's just that, like, see that? You can just flip these because we're in a commutative ring, right? Like, this is t0 plus s0, t1 plus s1, right? And that is literally tau plus sigma. And likewise, you can juxtapose the order of the coefficients in the next expression to show that the polynomial multiplication is likewise commutative. Also, the zero polynomial, right? Sigma plus 0 is equal to sigma again. That's clear. The polynomial with all zeros in it. That's also true. Now, so we can rewrite this in the following kind of sneaky way. So S0, 0, da, 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 all right, like that, plus S1, 0, sorry. So what I'm saying is you can break it into pieces, the sum of n polynomials, right? This is, so this nth or this degree n polynomial, right? I can write
As an addition of n different polynomials.
Yeah, I mean, technically, I'm counting wrong, n plus 1, right?
Yeah.
Possibly non-zero, they can't, I mean, the only one I know for sure that's non-zero is the last one.
Yeah.
I only know that coefficient's non-zero for sure because the degree is n. But then here's the thing, is you can prove that this is the same as like S0 with all zeros times 1, and then S1 with all zeros times 0, 1, 0, and then Sn with all zeros times 0, 0, 1, zeros. So this is, so in like linear algebra speak, you might think of the first one as like the first standard basis, and the second standard basis, that one. The last one, the one is in the nth spot.
You're missing a 0 on that. Wait, are you? Is that one's there? Oh, I see, okay. Yeah. You're scalar multiplying your units, yeah.
So this is a little bit sneaky step, but if you study the definition of multiplication, you'll see that I can factor those like that.
Mm-hmm.
So this is notation that I introduced in the notes. I say, all right, well, let me just, for the sake of simplicity, call that S0 vector times 1, 0, 0 repeated, plus S1 as a vector times 0, 1, 0 repeated, and then so forth. And I'll write the next one since I can now. S2, 0, 0, 1, 0 repeated. Eventually we get to Sn vector with 0 all the way to 1 in the nth spot, and zeros after that, right? Okay. So, sorry I'm using my phone today. I don't know if this is going to be visible for anybody else but YouTube. Sorry. Anyway, okay, well, what's the point of this? Well, let x equal to 0, 1, 0, and so forth and so on. All right. And we'll define x to the 0 power to be this one. All right. By the way, that polynomial that I just wrote, that serves as the multiplicative identity for polynomials, so you can check that. This right here has 1 zeros times sigma equals to sigma for all sigma in Rx. That's a nice homework problem. You can verify that polynomial times any other one gives you back the polynomial again. You just study the formulas, like these a sub k's. You've got, essentially the S1, rather S sub 0. S sub 0 is equal to 1. So when you look at the kth one, the only way to get k as a sum is 0 and k. So that just leaves you back a sub k, or rather it leaves you t sub k, no matter what coefficient you are. I mean, you could.
Yeah, S0 is the only term that's in all of them.
Yes. So that I'm just walking you through a sketch of how you prove this, but
yeah,
it's just the definition and thought through. So I'm saying x is 0, I'm introducing this notation, x to the 0 power should be that, and this is x. What's x times x? What is that equal to? So you work, think through it, and what you're going to get is 0, 0, 1, 0. Let me think through the powers with you guys just for a second and make sure I'm not just, talking past you. So 0, 1, 2, 0, 1, 2, the coefficients, right? So order 0 is 0. Order 1, I can either do, 0 times 1 or 1 times 0. So those are 0. Order 2, like A0, well, S0 with T2, or S2 with T0, those are 0 times 0, both cases. So only the S1 times T1 gives you what we call A2 as being 1, because 1 times 1 is 1. Okay. So takeaway message here, x squared is 0, 0, 1, 0. Guess what x cubed is in the meaning of x times x squared? So I'm proposing that this is x squared, by the way, definition. Yeah, so that's again 0, 1, 0 times 0, 0, 1, 0.
Take a guess and say it's going to be 0, 0, 0, 1, 0.
0, 0, 0, 1, 0, right. And so generally, x to the power n is I used n as a fixed thing up there, didn't I? So let me use something else, like x to the power k is 0, 0, all the way until we get a 1. And what slot is that in?
The third, or that's the kth slot.
The kth slot, that's the k
K
plus.
minus-
Well, I guess it depends on how we
Yeah.
define it, right? It is,
If it's S0, then that would be the K minus.
so this is the,
K plus 1.
if I, I'm sorry, I need to get some language here. If this is equal to, let's say, beta, and that has coefficients b sub,
Start with a naught, yeah.
b sub j or whatever,
Yeah.
then this is the basically we have b sub k equal to 1 and b sub j not equal to 0 for j not equal to k, right?
Yeah.
In other words, you could say that b sub j is the Kronecker delta jk,
Yeah.
which is 1 for j equals to k, and it's 0 for j not equal to k. Anyway, if you'll allow me to erase one of my lines, well, I think I can squeeze it in right here, okay? The point is, this is equal to S0 x to the 0 plus S1 x to the 1, if you will.
Mm-hmm.
Plus S2 x to the 2, S2 vector x2, x squared, plus S vector n x to the power n. Okay. In other words, I'm showing that you can express the polynomial as what? So thus, sigma in, oops, I'm not trying to keep it real just yet. Rx has form sigma equals to the sum j equals 0 to n of Sj vector x to the j. So at this point we're like, so we'll just write what? Okay, drop the vector, right? And we can then write sigma polynomial has the form what? Sum j equals 0 to n of S sub j x to the power j. And here we go. We have now come, to a rigorous underpinning of what we mean by polynomial and indeterminate. So do you understand why I say x is not a variable?
Yeah.
Like it's just kind of in your face here, right? Like look at this, here x is equal to 0, 1, 0, and so forth and so on, right? That's not a variable. It's a placeholder. So I'm making that explicit because I understand if you don't go through this like formal exercise, people can tell you, oh, it's just a placeholder, but that doesn't really have meaning. After experiencing this, you see what we mean by it's just a placeholder. Like we can make that undeniable. That's what this construction does. Now, there's yet better notation. So, alternatively, you can also write sigma is the sum, j equals 0 to infinity of Sj x to the j, where finitely many S sub j not equal to 0, right? And if you drop the condition that finitely many S sub j are not equal to 0, what you have then is a formal power series. Now I've circled back. That's why we call it a formal power series. It's a sum of, weighted powers of x with no condition whatsoever on convergence. That's what a formal power series is. Like, here's an example of a formal power series. You can have sigma is 1 plus x squared plus x cubed plus x to the fourth plus da 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 da, and so on, so on, so on and so on, forever and ever. Formal power series.
And yeah, you would just write sigma in that notation too.
Yeah. That would be a formal power series. No, there's infinitely many non-zero coefficients, right? And then you could then if you let, of course, then you can talk about functions of a real variable that have that formula, and that takes you to calculus too. Like that's a geometric series with radius minus x, so it converges on the absolute value of x being less than 1 for what it's worth. Or if x is a complex variable, it converges on the unit disk in the complex plane. All right, polynomials. This notation is very useful if you don't care about degrees and you just want to add them without talking about what their degrees are. Because, you know, if you want to add two polynomials in this notation, what's it look like?
Yeah, you can just skip all that mess.
Right, so sigma plus tau is just the sum,
Yeah.
you know, j equals 0 to infinity of s sub j plus t sub j x to the power j, you know, just that. And sigma tau is the sum k equals 0 to infinity of the sum j plus k, rather j,
I plus j.
thank you, I plus j equal to k of s sub I t sub j to the x to the power k. So that's what our definitions look like when you rewrite them in terms of the x to the power notation. All right, and there's no issue of convergence, provided that we only have finitely many of the s's and the t's non-zero. Now in calculus 2, you can study particular conditions that you can put on the coefficients if they're real numbers that will make these converge. And I think this is called the Cauchy product in that context. This example is important because this also drives home the point of why they're indeterminates and not variables. And because, like, I can say they're different, right? I can say they're different than polynomial functions, right? But this example really, really drives the point home in a more constructive way. So this example is important. 4.5.6. Here we have in Z3 x, this is polynomials with coefficients taken from Z3. You can look at f of x equal to x cubed plus 2x, and that is not equal to x to the fifth plus 2x as polynomials, right, an indeterminate x. Let's call this thing g of x. So these are certainly not equal as expressions, right? One's order degree 5, the other's degree 3, they're different. But check this out. F of 0, 0. F of 1 plus 2, which is 3, which is 0, right? F of 2, 1 plus 2 times 2, right? Which is 5, which is 2. Okay, how about G? G of 0, 0. G of 1 plus 2, 3, which also known as 0. G of 2, 32 plus 4, which is 36, which is, did I get that right? 2 to the 5th, 32, yeah. 36, mod 3 is what?
Mod 3 would be 0, because 3 divides 36.
Yeah.
Wait, so 2 to the 5th, that's 2 times 4, 8. Wait,
That's 0. Something here didn't go right. Oh, here it is. Look.
2, 4, 6.
What is 2 cubed? It's 2 cubed
That's
1.
8. No, not 1.
It's not 1.
Is
It's,
you know,
let's try this again here. 2 cubed
that's 8.
plus 2 times 2,
Which is 12.
which is 12.
Which is 0.
0. So these are the same function. If we view f as a function from z3 to z3, right? And g as a function from z3 to z3, where g of x, where with formulas given as above, in fact, those are actually both the 0 function, right?
Mm-hmm.
Kind of fine, but they're not equal as polynomials. All right, so definition, let R be commutative ring, all right, with 1. And then we define evaluation map for A in the ring by phi sub A of S sub 0 plus S1x plus da 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 plus Sn x to the n is equal to what? So I'm defining how to evaluate a polynomial. This is what we're all taught in pre-calculus, right? You take the x and you replace it with the a, right? So it's like S0 plus S1 times a plus da 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 plus Sn a to the n. So.
You might know a commutative.
Do I know a what?
They have caller ID, but they're from Oregon, and they've been to Oregon.
Yeah, me neither. Nothing against it, I just seems like a long way to drive. So this is how we can trade. I mean, this is the connection between, polynomial expressions and polynomial functions. Right? Polynomial expressions we can think of as living in the world of indeterminates. Polynomial functions, well, that's when you're actually thinking about putting a variable in, really thinking of x as a variable, But anyway, so let's see, your properties I should mention of the evaluation map. You can prove that phi a of, let's say, f of x plus g of x, right, is equal to f of a, well, excuse me here. We also like to use the notation that this is, oh man, I messed it up by curses. Gotta do some more writing. So we do like to use the notation, if we call this polynomial, say f of x, right, then we're going to define this to be f of a. So there's that. And And so with that definition, this works out to f of a plus g of a, which of course is, you know, phi a of f of x plus phi a of g of x. And similarly, if you have the evaluation map of a product, it is, well, it works out to, you can check this, it works out to f of a times g of a, which of course is the product of the evaluation maps as well. What does this say? And oh, one other thing. And also one other thing, phi a of the polynomial 1 is equal to 1. So here, properties, the evaluation map, phi a is a mapping from what, the ring to the polynomials over the ring, right? No, other way around. We take in a polynomial, right? And we output a ring element. So what happens if you've got a mapping, a function, right, that has these three properties? What does that say about the evaluation map?
Oh, it's isomorphism.
Well, isomorphism, maybe not.
Oh, wait.
But
Okay.
your heart's in the right place. So it's a ring homomorphism, right? So isomorphism, I would need to know.
It maps identity to identity.
Yeah, like isomorphism is unlikely because usually the set of polynomials are like in some sense way bigger, you know, than the ring itself.
Okay.
I mean, in some sense, polynomials are like vectors of arbitrary length over the ring, right? So
Yeah.
it's
Right.
those can have the same cardinality, admittedly. So
No, I should have thought about like not mapping certain things to certain things.
yeah, let's see here. So finally, a theorem. Theorem 4.5.8. If we have if D is integral domain, then polynomials over D form integral domain. So here's the proof. If f of x and g of x are in D of x non-zero polynomials, right? Then and let's say the degree of f of x is equal to n, the degree of g of x is equal to m, right? Every non-zero polynomial has a degree.
Are you saying int there for integral?
Integral, yeah. Here, I'll fix it. There you go. Then f of x, g of x, right? It's got, let's say, a n b m x to the n plus m plus stuff, right? So this is what we get from the product of the leading terms in those two non-zero polynomials, right? I'll give you the last term too, a0, b0, okay? So I'm assuming here f of x is the sum j equals 0 to n of a sub j x to the power j, and likewise g of x is the sum j equals 0 to m of b sub j x to the power j, right? That's the notation I'm using here. So what does it take to prove that, I'm assuming here D is an integral domain, okay? Assume D is an integral domain. That should be understood. So what am I worried about? I'm worried that f of x times g of x could be 0. If f of x, g of x is equal to 0, then, well, let's do it, right? Suppose f of x, g of x is equal to, 0. Well, that's equal to right, and the only way you can have the 0 polynomial is what? If every single last degree in the expression is 0, right? Every single coefficient has to be 0, but we only need to focus our attention on the the leading one. Consider that an bm is not equal to 0, right? Since an and bm are not equal to 0. And an and bm are elements of D, an integral domain, right? You can't have products of non-zero things in an integral domain be 0. Otherwise, you have 0 divisors, which contradicts the definition of integral domain. Consequently, f of x, so that thus f of x, g of x is not equal to 0, right? Which of course is a contradiction to f of x, g of x being 0. Which goes to show you can't have f of x, g of x be 0 when f of x and g of x are not 0. Which is to say that d of x is an integral domain. Theorem 4.59. Here we say let f be a field. Remember what that means. That means every non-zero element is also a unit. It's also a unit, right? It's commutative ring. Such that every non-zero element has a multiplicative inverse. And we'll pick f of x, g of x in the polynomials over the field. All right. With g of x not equal to 0, all right? Then there exists unique quotient polynomial and remainder polynomial. Such that f of x is equal to, q of x times g of x plus r of x, where either r of x is equal to 0, or the degree of r of x is less than the degree of g of x. We call q the quotient and r the remainder. All right, of division of f of x by g of x. I don't have a proof. I don't have the proof of this in my notes. All right, but I think I can describe it for you. So what you do is you the proof is here's a proof sketch. Okay, I'm not going to go through the details, but I'll just tell you a little bit about it. Consider this at S, right, which is the degree. It's the degree of f of x minus q of x, g of x, such that g of x is a polynomial over the field. Right? So it's not quite right. What's the problem with this? The degree is defined for everything except for what? There's one polynomial we did not define the degree of.
The zero?
The zero polynomial has undefined degree. There's a chance that f of x minus q of x, g of x could be zero. I need to address that somehow in this construction. So let's say this is not equal to zero, right?
Mm-hmm.
And
Wait, so the zero polynomial has indeterminate degree?
yes, it is not. We do not define the degree of the zero polynomial.
Because if it okay, well, I'm thinking.
That's a good question to ask. Why we don't do that? I don't have a good answer right off the top, but it has to do with like the formulas we write in terms of them being logically consistent. And I can't remember which one it is that makes it blow up.
Yeah, no, I can. I'm thinking only in like the real. I'm like, no, can't do that. So I'm just like, well, it's still a constant line. But it was like.
I never fuss over this issue in any class except for this one.
Yeah.
But anyway, so of course. So what's the other? So like. How can I say this? There should be like a preamble, right? If there exists
zero.
If there exists q of x such that f of x is equal to q of x, g of x, then identify that q of x is the remainder, and q of x is the quotient, and the remainder is zero. Otherwise, you can construct this set. I'm forgetting some technical nuance here, I think, but the long story short of it is this is a subset of what? It's a subset of the natural numbers and zero, right? Because you can have constant polynomials which have degree zero. And since that's a subset of the natural numbers with zero, then you can apply the well-ordering principle to pick smallest element, right? And so that gives you correspondingly a q of x and r of x, which then you can argue have the properties that you want. So it's an argument by well-ordering principle on the degree. You can also come up with a constructive argument in terms of actually the division algorithm on polynomials, I think, if you want. But anyway, I'm going to go on.
What does that say? Apply WOP to.
That's the well-ordering principle.
Yeah, to.
Element.
The smallest element of this, and then whatever the smallest element of S is.
Okay,
that's going to
I
inform.
didn't know what that notation was before smallest.
Oh, that's pick.
Oh,
I
okay.
can't.
I'm sorry.
It's okay.
I heard you talking and I looked up and I was like, I don't recognize
That's okay.
that. You couldn't read my notes either.
You're fine. Let me try to get on here. I want to wrap this thing up here before we're out of time. Let's see. So, corollary 4.5.10. Let F be field. polynomials over the field. Alright, then f of a is remainder in division of f of x by x minus a. And yeah, this theorem 4.59 is also called the division algorithm. Yeah. So the proof by division algorithm, there exists q of x and r of x such that f of x is equal to q of x times x minus a plus, well, r of x, right? But the degree of r of x is less than the degree of x minus a, right? If r of x is not equal to 0. So therefore, r of x is equal to a constant, which is not equal to 0 in that case, right? Otherwise, r is equal to 0, so f of x is equal to q of x times x minus a plus some constant, right? It's either 0 or it's non-zero, but that's what is given to us by the division algorithm. Considering both cases at once, they both leave us with a constant, either a non-zero constant or a 0, right? But what is phi a of f of x? Well, it's q of a times, well, a minus a plus c, right? Which is equal to c again, right? But that's also equal to, by our definition, f of a. So the remainder is f of a. Remember, I changed the notation for the remainder to c, but this is the remainder, right? And this, of course, is called the remainder theorem, right? The remainder theorem. Definition, f of field, all right, and f of x in the polynomials over the field, then c in f is a 0 of f of x if phi sub c of f of x, also known as f of c, right, is equal to 0. And then if x minus c to the k is factor of f of x, and x minus c to the k plus 1 is not a factor, then what?
You don't have some induction hypothesis?
Then, where was I? Then c is a 0 of multiplicity k. well, this is not good. Ay, ay, ay. So, so that brings us to corollary 12, which says what? F of field and A and F of X, polynomial of the field, right? Then A is 0 of F of X, right? If and only if X minus A is factor of F of X, right? And so I think I may have somehow just missed it in my writing today, but I don't know if I've defined factor. I think we've defined factor before, but just to be clear, what that means is what? What does it mean X minus A is a factor? That means that there exists Q of X and F of X, right? Such that what? Such that F of X is equal to X minus A times Q of X, right? In other words, you can divide F of X by X minus A and have remainder 0.
So okay, that's exactly what I was about to say.
And so it's immediately obvious then that that's the case if and only if A is a 0 of F of X, right? Because A of, that means, this means that of course F of A is equal to 0, and by the remainder theorem, well, F of A is the remainder. So it's this, you know, two different ways of, I would say skinning a cat, but I guess we're supposed to be talking about torturing puppies. Oh, I'm sorry, too soon? Let's see here. Check this out, F of X. So here's, the ring is Z2, right? Z2 is not a field, listen to me, Z6, right? Not a field. Why? 2 times 3 equals to 0, right? And if those are zero divisors are not units. These are disjoint categories. You can't have a zero divisor which is also a unit. You can't do it. So that means this is not a field, right? In fact, we know that only Z mod prime is a field, right? Anyway, so this polynomial, kind of funny, x squared plus 3x plus 2 has how many zeros?
2.
You say 2, I say let's find out.
X plus 1, X plus 2.
So f of 0, 2, f of 1, 1 plus the 3 plus 2, oh, that's 0. F of 2, 4 plus 6 plus 2, that's 12, that's 0.
Oh, already at 2.
F of 3, 9 plus 9 plus 2, which is
18, 21.
so that's 2. Okay, that one's not 0, right?
This is where I think we messed up. 16 plus 12 plus 2, 28, 30, and
30,
boom, out of here.
Also known as 0. 3 zeros. What? It's worse. F of 5 is 25 plus 15
plus 2,
also known as
42.
42,
And we're done.
which is again 0. So
What?
So this is a quadratic polynomial with 4 zeros. Right?
For what we know, yeah.
It is not the case. Like, this is not equal to x minus 1 times x minus 2 times x minus 4 times x minus 5, right? Like, that is not true. Because on the right hand side you have degree 4, but on the left hand side you have degree 2. You can't have that. So, remark the next thing. you know, the next corollary is a polynomial of degree n over a field has at most n zeros counting multiplicity. So if f of x is a polynomial over a field, right, and the degree of f of x is equal to n, right, f of field, then there exists at most n zeros, possibly repeated. And it's easy enough to understand that, right? Because each zero gets you a factor, right? Each zero gets you a factor. There's you know, there could be a number out here and out front, right? But each zero gets you a factor. What would happen if you had more than n zeros? You could factor the polynomial such that you had the product of more than n factors, but if you multiplied those out, you'd have an n plus 1th order term, which of course would contradict the order being n, right? So over a field, you can have at most n zeros. This is not a field. That's why we're allowed to have 4 for this degree too. I can tell you, I can testify to the fact that factoring polynomials over commutative rings is a far more subtle business than factoring polynomials over a field. Fields are very nice. Commutative rings, that's and I wouldn't know a thing about them if not for the fact that my research ended up going into that, just because like that's what it goes into. So, it used to be, I mean, some places it maybe it's still part of the standard curriculum, like polynomials over a commutative ring, but not always. So, all right, so that brings us to the last page in lecture 25, which I'll start again next time. Like the next thing up is principal ideal domain. That's something I need to do slowly and calmly and make sure we understand. It'll be with us the rest of the course, but. So sorry if this lecture was not particularly exciting. I mean, I'm mostly doing stuff you already knew in a more careful way, you know.